So starting off the chapter, we're going to take a look at 8.4. We're going to talk about angles of elevation and depression and our math humor for today. Why do mathematicians dislike the beach?
Well, because they have to sine and cosine to get a tan.
Well, so the angle of elevation is the angle that is formed by my horizontal up to the line of sight that would occur. So I've got an angle of elevation here. It's almost, think about it flying a kite. So you're down here in ground level. If you were to look straight forward, that's the horizontal. If I were to look up towards the kite, that's my line of sight. Now the angle that is formed by my horizontal and line of sight is called the angle of elevation. And I know it's an angle of elevation because I'm looking up. So anytime you're going in the upwards direction, you're working with an angle of elevation. If you're working in the downwards direction, it's the angle of depression. So that's the angle that's formed by the horizontal down to the line of sight. So think about it. If I was standing on top of a building and I was looking down at the street below, if I was just standing on the top of the building looking straight across, that's the horizontal. Down to the actual ground level, that's the line of sight. So from the horizontal down to the line of sight, that is my angle of depression. So angle of elevation is working up, and angle of depression is working down. So taking a look at the example here, what we need to do is name the angles of elevation and depression within our following diagram. So on our diagram, I've got an airplane, and the horizontal from the airplane is PD, and I've got the car, and our horizontal from our car is segment OC. So our angle of elevation is always from a horizontal up to a line of sight. Our line of sight between the plane and the car is segment PC. So if I'm going from a horizontal up to a line of sight, our angle of elevation would be angle OCP. So angle OCP is our angle of elevation. That's this one right here. And then for our angle of depression, that's from the horizontal down to the line of sight. So if I'm talking about my horizontal down to my line of sight, it's almost like I'm in the airplane looking down at the car. That's my angle of depression. So my angle of depression is going to be angle DPC. Now, I don't know if you noticed this, but technically speaking, since you're working with two horizontal lines, they're going to be parallel to each other. And if they're parallel, you've just formed a pair of alternate interior angles. We'll get into that in the next slide. So as stated before, we have horizontal lines, and horizontal lines here are parallel. And once they're parallel, I know that angle 1 and angle 2 are going to be congruent because they form the alternate interior angles. So by alternate interior angle theorem, angle 1 is congruent to angle 2. This kind of allows us to say that anytime you're working with an angle of depression and an angle of elevation, they are actually going to be the same exact measurement since they are congruent to each other. So let's go ahead and apply the angle of elevation to our problem here regarding the Seattle Space Needle. Now they're telling us that the Seattle Space Needle casts a 67-meter shadow, and the angle of elevation from the tip of the shadow to the top of the Space Needle is 70 degrees. So kind of imagine it this way. If I was standing here at the tip of my shadow and I looked all the way up to the top of the Space Needle, that angle of elevation is going to be 70 degrees. What we need to do now is we have to find out how tall our Space Needle actually is. Now this plays back on our SOHCAHTOA. If you remember, SOHCAHTOA. We currently have, holy cow, that is horrible writing. Horrible writing. Let's try this again. KAHTOA. Currently we have the angle of 70 degrees. And I know that I want to find the opposite to that angle. And I currently have the adjacent leg. So I'm looking at using O and A, which means tangent. So tan of my angle, 70 degrees, would end up equaling my opposite, which is Y, over 67. Now you know how to solve this, so go ahead, pause the video at this point in time, solve it out, come back, and we'll check our answers. All right, so let's take a look at this. I had tan of 70 equals y divided by 67. In order for me to solve it, I multiplied both sides by 67, so I got y equals 67 tan of 70. It did indeed say round to the nearest meter, so when I typed this in my calculator and I got 184.0809, I end up running to the nearest meter of 184 meters. So in our next example, we have an ice climber, and they're standing at the edge of a crevice. And that crevice is 115 feet wide. Now the angle of depression from the edge where the ice climber is standing to the bottom of the opposite side is actually 52 degrees. So we want to find out how deep the crevice is at that point, and we'll round that to the nearest foot. So what I'm going to do is I'm going to go ahead and draw out my crevice. So here's my crevice. Here's my person, my ice climber, okay? Now, we did say, there's my crevice, that it is 115 feet wide. So the distance from this point over is 115 feet. And the angle of depression from where she stands down to the bottom of the opposite side, we said, was 52 degrees. So we've got a right triangle here. And I want to find out what is the depth of my crevice. So I'm looking for the x value there. So now that I've set up the triangle for you, why don't you go ahead, pause the video, use your trig functions to figure out what the measurement of x is. Once you've got it, start it up again, and we'll check our answers. So let's go ahead and take a look at the answer here. I've got 52-degree angle of depression. I know the opposite leg, and I know the adjacent leg. So if I'm using opposite and adjacent, that's tangent, TOA. So tan of my angle 52 degrees equals the opposite x over my adjacent 115. So when I multiply both sides by 115, I'll get 115 tan of 52. And when I put in my calculator and round to the nearest foot, I'll end up getting a crevice that is 147 feet deep. Now in our last example here, we're dealing with a ski slope. And the ski slope is 550 yards long with a 130-yard vertical drop. Now what we want to do is we want to find the angle of depression. If you think about it, the angle of depression comes from the horizontal and goes down. But we said at the beginning of this lesson that the angle of depression and the angle of elevation are congruent to each other. So in my triangle here, the right triangle, I'm actually going to find out what this angle is, because as soon as I know what that is, I'll be able to tell you what the angle of depression is, since they are indeed congruent. So my angle of elevation and my angle of depression were congruent, so I'm going to find this angle down here. Okay? So I'm going to go ahead and label it with an X, and when I do that, I notice that I'm working with the opposite leg, and I have the hypotenuse labeled. So what we're going to do is we're going to use sine. Sine of my angle, x, equals the opposite, 130, over my hypotenuse of 550. Now remember, if you're trying to solve for your angle here, what we need to do is we need to sine inverse both sides. Meaning, when I sine inverse, I will end up getting x equals the sine inverse of 130 over 550. So if you put that in your calculator, and what you're supposed to do with this one is, let's go ahead and round to the nearest degree. I know it doesn't say it, but we're going to go ahead and do that. As soon as I put that in, I end up getting 13.67, but if I'm going to round to the nearest degree, I'm going to say it's approximately 14 degrees. All right, so if you have any questions on this, make sure to ask in class. Otherwise, have a great night.